So welcome back to the second session today. So we are happy to have Roberto Contino from Sapienza University, and he will tell us about accidental dark matter.
Can you hear me? Yes. Okay, so first of all, I would like to thank the organizers for having me here. It's really a pleasure to be again here in person in Florence. So my title is Accidental Dark Matter. The plan of the talk is the following. So first I will give some motivations and explain why accidental symmetries, and in particular the accidental stability of dark matter candidates, is interesting. I will explain how this idea works, first in the case of particle dark matter, and then I will also discuss, if time permits, the case of the accidental axion. So motivations. We know that the standard model has to be thought as an effective field theory with a renormalizable Lagrangian plus higher order terms. And if we restrict to the renormalizable part, then we see that there are accidental symmetries which emerge, especially if we think of in the renormalization group flow at low energy, only the renormalizable part is important, and these symmetries are really emerging. Symmetries which you don't ask for, but they come to you for free. For example, baryon number and lepton numbers are the most important ones, at least for our discussion. But there is also an approximate custodial symmetry and approximate flavor symmetries, but which are also very important for the standard model. All these symmetries emerge at low energy, and they are violated by these higher dimensional operators in general. In particular, we know, for example, that the lepton number must be violated by a dimension 5 operator if you want to explain neutrino masses and oscillations. In the case of baryon number, this is particularly important because it leads to the stability of the proton at the cosmological level. And this symmetry is violated by dimension 6 operators, which mediate proton decay in this way. Now, cosmological stability would require that these operators appear at a scale at least as high as 10 to the 10 GeV, but bounds from super Kamiokande imply a much stronger limit, around 10 to the 16. So this idea of accidental proton baryon number and proton stability is very successful and elegant in order to explain why we are here, why protons are stable. Now, if we look at the budget of the universe, ordinary matter only is only a 5%, around 5% of the total, and the stability, accidental stability of the proton explains this 5%. Now, it's natural at this point to ask whether the other 26%, which should come from dark matter, could also be the result of an accidental symmetry. Okay, I think it's very natural. Of course, this assumes that this dark matter either comes in the form of a particle or of a field, like, for example, in the case of the axion. Now, accidental symmetries are nice because we think that eventually gravity will violate any global symmetry, at least at the non-perturbative level. So if you impose this symmetry by hand, for example, like in supersymmetry or in any other scenario in which you ask for a symmetry which stabilizes the dark matter, eventually this symmetry will be in clash with non-perturbative gravitational effects. In particular, arguments based on black holes will give you a breaking eventually of the global symmetry. So accidental symmetries, which are symmetries which emerge at low energy and they are violated in the UV, are particularly interesting in this sense. So let's see how the idea works for in the case of a standard particle dark matter candidate. So the cartoon here is that of the standard model sector, in which we also include the Higgs, neglecting the hierarchy problem. And then we postulate that there is some additional dark sector, which is coupled, could be coupled to the standard model sector in a variety of ways. First, of course, it has to be coupled through gravity, because we have detected dark matter. Dark matter is in the dark sector, but there could be other connections, like, for example, portal interactions, if this dark sector is completely neutral under the standard model, or standard model gauge interactions if some of the constituents here are charged under the standard model gauge symmetry. So this dark sector is postulated to include the dark matter candidate, but it could include also many other fields. Okay, there is no reason why it should contain only one particle and nothing else. Now, we want this dark sector to have this accidental symmetry. Okay, some symmetry which is emerging in these dynamics at low energy. If the symmetry is broken by an operator with dimension d, then you can estimate the rate of decay of the dark matter candidate very easily in this way. And now, cosmological stability imposes bound on the lifetime around 10 to the 10 years. But then there are bounds, similarly to the case of the proton stability, there are much stronger bounds coming from indirect detection, CMB, 21 centimeter line, and so on, which impose a constraint on the lifetime at the order of 10 to the 18 years. So now in this plot here, I'm showing the minimum value of the UV scale at which this operator is generated as a function of the dark matter mass in two cases, when the dimensionality is 5 and the dimensionality is 6. Okay. Now, if the dimensionality is 5, then you get a bound. You get that if the scale is over the lambda UV is over the of the Planck scale, then the particle mass, the dark matter mass, cannot exceed something like 100 keV, okay, 10 to the minus 4 GeV. So it has to be lighter than this value. Otherwise, this rate of decay will be too large, and then you decay too early, and this will be in tension, in contrast with these bounds. Instead, if the operator has dimension 6, then the mass can be much higher. Okay, of course, the proton is something in between, and the bounds are more stringent. In the case of dark matter, you can allow yourself to, if the operator has dimension 6, to go up to 100 TeV of mass, and that would work. Okay, so for a violation of the protecting symmetry at the level of dimension 6, then you can have and if the operator is generated at the Planck scale, then the mass of the dark matter can be as high as roughly 100 TeV. Now, there are many candidates. There are many kinds of different candidates for dark matter, accidental dark matter. I know of basically only one, at least a successful one, which is minimal dark matter in the case in which the dynamics in the dark sector is weakly coupled. That has been proposed by Cirelli, Fornengo, Strumia some time ago. And then there are many other possibilities instead in the case in which the dark sector is strongly coupled. So there is dark matter which could be formed in terms of dark baryons, of dark mesons, dark pions in particular, exotic possibilities like the group work, which I will discuss. And then there is also the possibility of having an accidental action, which I also mention and discuss. Here, the accidental symmetry in these cases is either a U1 symmetry, like for example, dark baryon number in the case of dark baryons, in analogy with QCD and the proton, or it could be simply a parity, a dark parity. In the case of dark pions, we will see that there are species numbers which stabilize these mesons. Now, by dark sector, I will mean in this talk a gauge theory with gauge group GD, and dark quarks, fermions, dark fermions, which transform as some representation both under this gauge group and under the standard model. Of course, this is an assumption. And the assumption, of course, is there are two possibilities. Either this sector is neutral under the standard model, then it will become much more complicated to see, to probe it and to discover it. Other than, of course, the manifestation of dark matter itself. Or the other possibility is that some of the constituents of this dark sector are also charged under the standard model. And that is the case that I want to, more optimistic case that I want to discuss. So I will assume that in this group GD, there is a subgroup which confines, and I will call it dark color. Okay, that's the way to form bound states among which there will be the dark matter. So one important assumption in this story is that the dark quarks transform under the standard model as vector-like representations. That's useful because it's important. Actually, is basically mandatory. Otherwise, you will get very large corrections to electroweak precision observables. Okay, and then these theories will be ruled out. Basically, there will be technicolor theories, which are, as we know, in tension with data. So these representations will be such that this little r, the representation under the standard model, must be vector-like. Okay, let's look at the first example. This is a theory in which the dark matter candidate is a dark baryon. And the example is taken from this paper by Michele and collaborators, in which they consider 3 species which transform as fundamental representations of the dark color. 2 of them form a doublet of SU2 electroweak, okay, with this given upper charge, and they call it L because they have the same quantum numbers as a lepton in the standard model, and then a singlet. Okay. Now the Lagrange, these are the quantum numbers written in two-dimensional, two-component formalism for Weyl fermions, which are taken, for example, to be left-handed. And the Lagrangian is written in 4-component notation. And you see that, of course, there is a possible Yukawa coupling that you can write with a Higgs. Now, the accidental symmetry in this case is dark baryon number, okay, under which all the 3 guys here have charge 1, and the conjugated fields have charge -1. So exactly in analogy with the proton in the standard model. The dark matter candidate, unless you take very hierarchical masses for the L and the N, is a total singlet formed by NDC, where NDC is the number of dark colors, singlets, and it has a spin NDC divided by 2. Okay, it's a baryon which is a singlet of the standard model. Notice that this is an example in which the representations are vector-like also under dark color. So the theory will confine, it's like QCD, and everything is under control. Now, the cartoon for the spectrum is the usual one. So at the scale of confinement, there will be some baryons, then there will be mesons with spin 0, spin 1, etc. Then, separated by a weak loop, there will be non-Bogosson bosons of this theory. By the way, I'm considering this case the situation in which the masses of the dark quarks are lighter than the dynamical scale. For illustration, there is also the other limit, but I will show it. I will discuss it for another theory. So here, let me assume that the quarks are light. Okay, the dark quarks are light. So there will be non-Bogosson bosons. Some of them will be charged, and then we get a mass at the one loop level from gauge interactions, standard model gauge interactions, and there will be other states which are neutral. Now, the dark matter resides here in this sector, and it's the lightest baryon, in particular the singlet, as we saw. These baryons, and I will annihilate with anti-baryons in the early universe into mesons. Everything here is dark, of course. The cross-section is large, is of order of the geometrical cross-section. It goes like 1 over the scale, dark sector scale squared. And if you want to reproduce with this the thermal abundance, which is implied by this cross section, the dark matter density, then you have to set this dark scale to be of order 100 TeV, which is exactly at the edge of the interval, which is allowed to have an accidental stable particle, as I said at the beginning. So it works. Okay, so the scale will be of order 100 TeV, and the scale of the pions, the dark pions, will be of order 10 TeV. Okay, so pretty heavy if you want to discover them at the colliders. And in fact, these guys are produced via Draian in pairs, and then they will decay either through anomalous couplings, which are generated in one loop, or the Yukawa couplings. You might want to produce the lightest states, which are the standard model singlets, but this is tougher because, of course, they don't couple directly, except for their anomalous couplings, which are suppressed, of course. So it will be more difficult to produce. The cross section will be much smaller, and or they can be produced in decays once you first produce the charged ones and then the decay to the neutral ones. So these are the strategies to produce these guys, but of course it will be difficult because even a future colliders, because of the scale. Now let me show another example, which I will dub the glue quark, in which the theory is more exotic. So there will be, again, 3 flavors, but now of dark quarks transforming as an adjoint of dark color. Okay, and they will transform as a triplet of SU2. So this is a case in which the representations are real. Now, the Lagrangian at this point at the normalizable level is this one. Okay, there are no Yukawa couplings that you can write, and which means that since the representations are real, you only have a dark parity at the level of accidental symmetries at this level. So there is no U1, but this is still enough to stabilize the lightest odd state, which is a bound state formed by one quark and glue and dark glues. This I will call it glue quark, and of course it inherits the quantum numbers under the standard model of its constituent quark. Okay, so it will be a triplet with 0 hypercharge by assumption, and in this triplet there will be a component which is neutral under the standard model, and most likely will be the lightest of the 3 after the gauge interactions of the standard model are taken into account, and that's the dark matter candidate. Okay, so it's a singlet which comes from a triplet, which is a bound state of this new dynamics. Now, at the time we wrote the paper with Michele, we were looking at the situation concerning the lattice simulations for theories with adjoint fermions, and this is the table that we made. So there is some information, some properties known for number of colors equal to 2, and some smaller set of works for and colors equal to 3. And but for larger number of colors, we found nothing. So in the following, I will discuss the case in which the mass of the quarks is higher than the dynamical scale, and that's basically okay, even if the number of flavors, which in my example was 3, is so large that we lose asymptotic freedom. Okay, in this theory, asymptotic freedom is lost for NF equal to 6 for 6 flavors, and for NF equal to 5, you have a fixed point in the infrared, which is perturbative. So even in these cases, you can evolve down your theory, which will stay weakly coupled until, of course, you reach a scale of order of the mass of the quarks. Then you integrate all the quarks, and the theory will confine. So this situation is the one that I will discuss. If you instead want to look at the cases in which the mass of the quarks is lighter than the dynamical scale, of course, you have to be in a confining regime, which might be possible even for NC equal to 3 and the number of flavors equal to 3 or smaller. Now, let me focus on MQ, so the mass of the quarks larger than the dark sector scale. And that's the cartoon for the spectrum. Of course, again, we have baryons as the heaviest states, but this time their mass is of order NDC times MQ because of this assumption. Then there are mesons at energies of order 2MQ, and then there are glue quarks which have mass of order MQ. Now, the mass of the glue quark was computed on the lattice, of course, for different purposes. These are the papers that we found. So there is already some information, okay? But of course, lattice is crucial, both in this case and the previous case, to determine all the properties of the dark sector and the dark sector asymptotic states. Now, glue quarks are stable due to the accidental parity, which is broken at the level of dimension 6. This is the operator that you can write. Basically, it's an operator made of a quark and the dark gluons, which transforms as a triplet, and then you multiply times another triplet made of standard model fields. And the decay of the glue quark is, which is interpolated exactly by this operator here, is to a Higgs and a neutrino. That's in the heavy quark regime, which I'm studying here. That's the main channel, and this rate, of course, you can estimate in a heavy quark limit in a perturbative way. In this case, like the 5th power of the quark mass. Okay, that remember this because we will use it later. Now, it's important to notice, and it's very interesting to notice that this object is the glue quark is different from, for example, from a heavy dark baryon, because it has a constituent quark which is very heavy with mass of order MQ, which is much larger than the dynamical scale. But then it has a cloud of dark glue around, which makes its size to be of order 1 over lambda dc, much larger than 1 over MQ. Okay, so it's a heavy state, but also very large, and that is important for its cosmological evolution. Let's sketch it very quickly. So at the time, at the temperature of order the mass of the quark, dark quarks have a first perturbative freeze out, which freezes out their number. The cross section is the perturbative one. But then after confinement, these glue quarks form, and they basically get all the use all the dark quarks which are left over, and there is a certain abundance of these glue quarks, which, however, can interact again and annihilate again through a process which we call the recombination process. Recombination because you have to imagine that these two of these glue quarks come together at a distance of order 1 over lambda dc, and they form by recombining their constituents, they can form an excited Q meson, if you want. Let's call it a meson, a state made of 2 quarks plus, of course, plus glue, which has a size again of order 1 over lambda dc. This state can go down, de-excite, go down to the fundamental level by emitting glue balls, dark glue balls, and once it has reached its fundamental level, then it can decay into glue balls, which then eventually decay to standard model. So this is a process in which you start with 2 glue quarks and then you end up with the standard model. So it's a way to annihilate, but it's not a direct annihilation of the 2 constituents, which would have a cross section of order 1 over MQ squared, which is much smaller. It's a process with a cross section which is much larger. It goes like the inverse of the size square, the radius square of this bound state. Okay, so of course, in order to compute this rate, you need eventually some non-perturbative tool, and lattice here again would be very important. So this is a very short summary of the results that we found. So the dash in the plane of lambda DC versus MQ. So the dashed line is the line in which we reproduce the thermal dark matter abundance. So the dark matter abundance through thermal abundance of this glue quark. In particular, the vertical part is the part of the curve in which the mass of the quark is smaller than the dynamical scale, which basically is the same regime as I discussed for the case of the dark baryon. In which case, the annihilation cross-section is set by lambda DC, and in order to reproduce the dark matter abundance, you need lambda DC over there 50 or maybe 100 TB. Okay, but then if the mass of the quark becomes heavier than the dynamical scale, then you follow this curve, okay, which has very interesting processes occurring, which I don't have time to discuss. Now, in this plane, we already have regions which are excluded. The first is an exclusion coming from the fact that glue quarks can annihilate today, okay? Again, with a cross-section which is very difficult to compute. It's the same process of the recombination that I was discussing before. Now, this process, of course, is the same, but it's also different in the sense that the velocity now is much smaller. So it will occur in a different regime. Here we are assuming that the cross-section has this size, which is the size of the final bound state QQ in the fundamental state. But we consider also another ansatz which led to different results. So there is a big uncertainty which can only be resolved by a non-perturbative calculation. So in this under this assumption, which is conservative, we ruled out this corner of the parameter space, because once you have these annihilations, you will produce neutrinos, photons, which can be observed and exclude this corner of the parameter space. The blue region instead is excluded by the fact that the glue quark can decay through dimension 6 operator. And we saw that this dimension 6 operator with 100 TeV glue quark mass is already borderline. So this is the manifestation of the fact of being borderline, that you can exclude an important region of the parameter space. Of course, the rate of decay scales with the mass to the fifth, which means that higher masses will be excluded. And here again, you can use the CMB, the 21 centimeter line, and neutrino experiments looking at neutrinos. I will skip here. Of course, you can also try, I will go very fast here. You can also try to hope and discover these glue quarks and the other particles in the spectrum in the collider, but this is very tough because of the energies involved. So these guys are very, very heavy. Okay, so either you can try either to produce mesons, in particular on resonance, or to open produce the dark quarks. Okay, and which eventually hadronize into glue quarks, and then since this is a triplet, it can the charge component can decay to the neutral component, and there is a splitting which is due to electroweak corrections of 160 MeV. This gives you a pion which is very soft, and it goes on is not detected. So you have a disappearing track, and this will give you bounds which can reach something like 8 TeV at FCC. Okay, but this is still far from the region in which you can reproduce thermally the dark matter abundance. Now, okay, let me switch gear and try to discuss the case in which the dark matter is a dark meson. Now, here the situation is less simple, because in general, you can use dark number species to stabilize this meson. For example, suppose the meson is made of a quark Q1 and Q2. Okay, these are two species. Now you can consider a symmetry under which Q1 has charge -1 and Q2 has charge +1. Okay, this of course is a symmetry under which the meson is odd, and if the symmetry is accidental, this species number is accidental, then this will stabilize the meson. However, given the fact that this dark matter candidate has to have zero hypercharge, otherwise it couples very strongly with a Z, and then you would have seen it in direct detection, which means that it has to have an integer isospin, because otherwise it would be electromagnetic charged. Then eventually, given these constraints on the quantum numbers, it's always most reasonable models and situations is always possible to write dimension 5 operators in addition to the mass terms, which violate this symmetry. So this symmetry is broken by dimension 5 operators, at least in the majority of the cases, which is not enough. Okay, it's not enough to stabilize this particle. An analogy of a dark of species number stabilizing particles comes from the standard model. Consider QCD with 2 flavors. Okay? You can also gauge the electromagnetism. And this is if you want, the quantum numbers, if I write everything in terms of Weyl fermions. Now here you have at the global level, you will have a symmetry, which is SU2 left crosses SU2 right times the barrier number, which is spontaneously broken to isospin, but eventually explicitly broken to electromagnetism times U1 3V, which is the accidental species number under which the up and down have opposite charge. Now, this species number would make the pion stable, the charge pion stable. Of course, pi 0 decays through the anomaly, but pi plus and pi minus would be stable, except for the fact that this species number is broken by dimension 6 operators, which are generated by W exchange. Okay, so this is exactly the situation that we would like to have. So operators generated at the dimension 6 level. Unfortunately, if you try to reproduce this scheme for dark matter, now you have the Higgs. Okay, so suppose now you have a dark color. You write again something very similar to what we saw for QCD. The weak gauging now is not electromagnetism, is SU2 electroweak. Okay, and now you will have 4 flavors. So you have SU4 times SU4. Eventually explicitly broken down to SU2 electroweak, and then there will be a barrier number, dark barrier number, times the species number. Okay, again, under which psi1 and psi2 have opposite charge. This is the accidental symmetry, okay, global symmetry. So you have 15 Gaussian bosons, but all of them will decay through this dimension 5 operator. Okay, and this, of course, is different from the case of QCD because now you have the scalar, which is the Higgs, and you can write the dimension 5 operator. This is exactly the problem that I was mentioning before. Now, a way to solve this problem is by introducing an extra U1 dark gauge and choose the charges in such a way that the representations are chiral overall. Because at this point, if the representations under the gauge group are chiral, then you cannot write neither the mass term nor this dimension 5 operator, which is a bilinear in the fermions. Okay, so that's the trick that we propose in this paper, and yeah, I will discuss this theory in the next couple of slides. So this theory has, this is the dark gauge group. You see there is a dark color times a dark U1, which is spontaneously broken, is X at the scale of dark confinement because it has chiral charges. Of course, this A cannot be equal to 1, otherwise you will have vector-like representations. What are the other parameters? The other parameters is the dark charge for U1, the dynamical scale for the dark color, and then because of you have a U1, you can also mix with hypercharge. So you will have also a mixing parameter, which I call epsilon. Okay. The symmetries are those that I showed before. So there is this symmetry, which is accidental. There is a U1 3B and U1 dark baryon, which stabilize, these two U1 stabilize 2 different particles. One is the dark baryon, okay, so which we still have. But then this U1 species number U13B will stabilize one of the Nambu-Gosson bosons. So the Nambu-Gosson boson decompose in terms of the SU2 standard model as 3 triplets, and then you have singlets. Okay, so these are pseudo because they are charged under either SU2 electroweak, the triplets, or U1 dark, this U1 plus minus. The U10 is eaten by the U1 dark and makes a massive dark photon. And this U1 plus or minus is stable. It's stable because it's charged under U13B. Okay, these plus or minus are the charges under U13B. And that is also a dark matter candidate to get together with the dark baryon. That's a cartoon of the spectrum. So you have the baryons. Okay, very good. So of course, the baryons should not be charged under electromagnetism, otherwise you are lost. Okay, and this it implies that the number of dark colors, since the constituents are doublets under SU2, you cannot have an odd number of constituents, which otherwise you will get half integer isospin and non-zero electric charge. So the number of dark colors has to be even, and if you don't want to have Landau poles for the standard model too early, you have to confine yourself to 4 or 6. Okay. Then there are the Nambu-Gosson bosons. So there are the triplets, the singlet, and they will acquire mass at one loop. Okay, these are the estimates that you can do. Again, here, in order to compute all these quantities, you need some non-perturbative tools. So again, lattice would be important. There is also an hyperfine splitting here, which I mentioned before, between the charge and neutral components under SU2 electroweak of the triplet. Sorry, under electromagnetism of the triplet. This is the splitting which you get, which can be computed, is calculable. And then there is the dark photon, which can decay only through the mixing epsilon, the epsilon mixing parameter. And if this epsilon to standard model particles, if this epsilon parameter is small, then this gamma dark will be long-lived. Okay. Now you can repeat the analysis of dark matter or accidental stability of the particle species number, and you get that depending on the number of the value of A of this charge A, then the breaking operators can have a very high dimensionality. Okay, basically only A equal to 0 gives you D equal to 6, and then you get higher and higher operators very easily. Okay, while baryon number is broken either at dimension 6 or larger level. There is also there are also discrete symmetries. In particular, there is a dark charge conjugation under which fields transform in this way, which makes small values of epsilon technically natural, because this dark charge conjugation is broken only by the kinetic mixing. So if you take epsilon small, it will remain small naturally. Okay, and then there is also G parity, which is broken by the U1 dark gauging. So this is a summary of the results in the plane in which you have the mass of the dark matter versus the mass of the triplets. So the red line is the curve in which you reproduce thermally the dark matter abundance. Above, you are excluded because you have too much dark matter. And then there is a band in which you are excluded by dark pion annihilation. Sorry, I had to say again that there are two dark matter candidates. One is the dark pion, which annihilates two dark photons through this diagram. So that's the cross section. And then there is also the dark baryon. Okay, so annihilations today of these dark pions lead eventually, once the dark photons decay into standard model, lead to photons which you can see, and this is the exclusion today around 100 GeV. Okay. Then there is an exclusion coming from production of the triplets, which are the partners of the dark matter. Dark matter is neutral under the standard model, at least the pion, but it has partners which are triplets under SU2, and here you get a variety of exclusions from the LSE. okay, which remove this blue band. So you see that, again, this is a model which is under test. You can exclude a significant portion of the parameter space. Now, for the future, you will have FCC, which can exclude all these portion here. So we'll test a lot of this parameter space, and also the Cherecom array, telescope array. So we'll looking at photons from the galactic center, will be able to exclude all this portion of the parameter space on the left. Okay, so again, this is a nice interplay between complementarity between direct searches at the LHC and indirect searches from celestial observations. Okay, I think I still have 5 minutes. Perfect. So I will go very quickly on the accidental action. So accidental action, you know, is a pseudo-Navier-Stokes boson. The action is a Navier-Stokes boson of a Peccei-Quinn symmetry, which is broken by instantons effects. And this contribution here will give a potential at the scale of QCD. And then if there is any other term which violates, in addition to the instanton effects, the Peccei-Quinn symmetry, that has to be sufficiently small, not to be in clash, not to be excluded by neutron electric dipole moment measurements. Okay, so these theta at minimum has to be smaller, as you know, than 10 to the minus 10. Now, the question is, can the Peccei-Quinn symmetry be accidental? Of course, the Peccei-Quinn symmetry is stabilizing the action in the sense that the decay arises through the instanton term, so the dimension 5 operator originating from instantons. But then there is also so that symmetry is broken at dimension 5 level. But other than that contribution, in fact, the constraint coming from EDMs is that there should be no other operators, no local operators in the UV theory which break the Peccei-Quinn to much higher precision, much higher dimension. And this is because if you have such an operator in our story, the action will be composite, so there will be some constituents psi. So if you write this operator with n some power, this fermion bilinear, then you will get a delta theta estimated in this way, and this has to be smaller than 10 to the minus 10. So this bounds excludes the portion below these lines. This is if the operator is generated at one loop, okay, with a naive estimate of the coefficient, or 3 level. And you see that because this is a plot of this dimensionality of the Peccei-Quinn operator versus the decay constant of the action. Now, the constants of the action smaller than 10 to the 8, 10 to the 9 GeV are excluded by supernovae bounds, which means that the dimensionality of the Peccei-Quinn violating operator has to be at least larger than, let's say, 9, around 9. Okay, so which makes the story, the game, much tougher compared to the dark matter, particle dark matter story. Okay, so this goes under the name of action quality problem. Now, if you instead further, if you want to require that the action has to have a decay constant of order 10 to the 11, 10 to the 12 in order to explain dark matter to the misalignment, then this requires a much higher dimensionality, okay, of order 12 at least, if not more. So this really makes put under pressure, under severe test, the idea of Peccei-Quinn as an accidental symmetry. Now, the question is, can we use our theoretical tools and build a model which satisfies these very tough requirements and break the Peccei-Quinn symmetry apart from instanton effects only at the dimension 12 or larger values, dimensions? The answer is yes. For example, we put forward a model in which, again, you have the same scheme as before. So you have this U1D, which has charges, complex charges, which make the representations complex overall. Now, of course, you need at least 3 reducible representations because you want to have the axion. So you have the minimum number is 2 Goldstone bosons. One is eaten by the U1 dark, and one has to be the axion. Okay. Of course, there are tough requirements. You have to cancel the anomalies, and then there has to be dark color confinement. You don't want to your standard model gauge couplings to blow up. And then we came up with only 3. Sorry, I forgot to say that now I want to construct a GATT model. So the representations under the standard model actually are representations under SU5 GATT. Okay, they are improved to GATT representations. So we found only 3 possibilities. Okay, in which there is a minimum value of FA, okay, and a certain range of number of dark colors in order to satisfy all these constraints. In particular, let me flash in one slide the properties of this model here, 1, 5 bar 10, because these can have FA as small as the experimental bound. So here there are several charge assignments, okay, which give you violation of the Pechequin symmetry at the level of dimension 12, okay, which is enough to solve the axion quality problem. There are interesting, what are the predictions of this theory? Of course, all these dynamics is at the Pechequin scale, and it's very, very high, okay, because at least FA has to be over the 10 to the 8. But there are other two states which are pseudo-Nambu-Goldstone bosons, which come because when you break the GATT symmetry down to the standard model, the number of irreducible representations goes from 3 to 6. Okay, when you break the SU5 representations to standard model representations, then you have additionally 3 Goldstone bosons, which of course get masked through GATT effects of this order. And now the energy cartoon is the following. So you have MGAT. We postulate that lambda DC, the Pechequin scale, is below MGAT, where you have all the heavy states. Then there is a gap between lambda DC and FA, which again could be computed by lattice. That's important, in fact. And then there are these 3 light states, which are in principle much lighter than FA. And then below there is a Latrobe scale, and eventually the axion mass. Okay. Conclusions. So I think that accidental dark matter is an attractive framework. Okay. So there are, of course, the drawback is that there are many possibilities, and in particular, if you postulate that the dark dynamics is strongly interacting, you have many dark matter candidates. So dark baryons, glue quarks, pions, and even axions. Okay. Now, the phenomenology again is very diverse. So you can have dark matter with a large mass beyond the unitarity limit for reasons which I did not discuss. So much larger than 100 TeV, or it could be in the TeV limit and be connected with other charge states, state charge under the standard model, which lead to collider signatures, which could be seen at the future colliders. I think that the current models are interesting, but they're not completely satisfactory to me because of the not completely convincing connection with grand unification. I think that's the weak point of this story. Maybe except for the axion model, the last axion model that I presented. The other models are not fully, I wouldn't say compatible, but the story with grand unification is not complete. And the last remark is that lattice simulations are really important here. So if any of these models turns out to be real, then there will be a plethora of quantities which should be computed on the lattice. And in particular, here is a list depending on the model. So there is a spectrum. So there are the annihilation rates. There is this process of recombination, which sets the dark matter abundance, and also the rate of indirect detection. There is also the question of whether, in the case of theories with adjoint quarks, chiral symmetry is broken at all or not for light quark masses. self-interactions of the dark matter. I mean, you name it, and it's in the list. Okay, thank you very much.
Thank you very much, Roberto. So we have time for a couple of questions.
Yeah, thank you very much, Roberto. You really have prepared, I think, the perfect talk for this kind of audience.
Thanks.
But still, we need, I mean, I don't know how to handle this, because we will still need more guidance. I mean, of course, the Lattice community, speaking for myself, we would love to contribute to this program. As you said, there is such an enormous variety of models, and we should need some help to understand which ones are more important for you to look at,
right,
and especially which ones we can actually do, because the models you have mentioned range from at least affordable with our means to next to impossible.
I know.
So, okay, you can't handle this now, but I just want to say this would be
Yeah,
an important point in our discussion.
Let me say that it's difficult, I think, also for me as a model builder. I don't know whether the same feeling is shared with by the others, but it's difficult for me to highlight things which are more important than others. I would say that the models can be divided, at least this is what I think, in two groups. Those in which you have the accidental stability, okay, and those in which you don't. For example, models in which dark matter is a dark pion, and you have operators at the dimension 5 level, those are not accidental. You have to put the symmetry by hand, or hope that the UV theory is kind with you. Okay, so there is a lot of work on this, okay, even by Lattice people, which I have not reviewed. But of course, these are valuable models and interesting studies. But so today I discuss about accidental dark matter. So for accidental dark matter, again, so it's tough because the models, for example, for the glue quark, I like it a lot, but there is a problem that this model apparently cannot be upgraded to a GATT theory. It's not possible because otherwise there would be too much math, so we couldn't figure out. Okay, and also in particular, the problem is even more severe for the chiral model with the meson, because there the representations are chiral. So there, I wouldn't say that it's hopeless, but it's very, very tough. Okay, because either you put all the fields from the very beginning, okay, and so the only possibility that we found is in the case in which you have a 5 of SU5, but that contains, unfortunately, states which contains basically an axion which, however, gets contribution from its mass, also from the GATT states. So eventually there is no parameter in which you are safe. Either you make it too light and then you get the dark matter from the pions, but then you're excluded by axion searches, or you make everything heavy, so you pass the dark matter, the axion searches, but then you have too much dark matter from the pions. So this somehow it's a model in which you cannot reconcile. Other GATT models we haven't found. So of course you can study that model, but I would feel somehow uneasy to suggest you that. Maybe the models which stand better in this time are those in which the dark matter is a dark baryon, studied by Michele. I think there again the GATT story has to be more studied, and this is what I'm doing in this moment. And these are even simpler because I mean dark baryons are more familiar. And also there is a lot of studies to be done, in particular for the annihilation cross sections, both in the light and heavy quark regimes. There are key quantities apart from the spectrum which need to be computed. Okay.
So if I can make here,
I think it's now it works.
Okay. Now, in this lit opinion, the most dramatic is the question if you can have confinement without chiral symmetry breaking.
True.
which is discussed in the context of this glue quark theory, and will literally give a new